3.
Okay, Assalamualaikum and greetings to Dr. Jila and Mr. Friend. So today we are going to do the video recorded that is about our subject heat transfer, PMMT 218. So we are from group 1 that consists of 3 members, Muhammad Irfan, Faiz bin Muhammad Jasni, Sariza bin Zidek, and Abdullah bin Abdul Wahab. So we are going to cover about two things. That is first the application in daily life, and secondly is the application of heat transfer in industry. So first, we go to the daily life application, that is ironing cloth. Alright, we will first see the visual graphic visualization of ironing cloth. As you can see, the person is ironing cloth, and you can see the wicker from the fabric goes off. And this video also give you some reminder that to stay focused during ironing cloth, because if not, it will cause the cloth to burn out. Alright, next slide. Alright, I will talk about the heat transfer concept and process in the ironing cloth. So, what type of heat transfer is involved in ironing cloth? So, the type of heat transfer that involved in ironing cloth is conduction. And because in this case, the heat is transferred to the fabric by the conduction process, where the direct contact occurs between the plate of iron and cloth surface. You can see the heat energy move from the hot surface to the lower temperature surface from the iron plate to the cloth. So how does an iron work? So basically, first we plug on the iron, and then after a few minutes, the metal plate of the iron become hot, and then we apply the iron on the wicker fabric. After that, when we apply it, the heat weakens the molecule bond on the fabric, and finally the wrinkle are removed from the fabric. Alright, and then we move to the calculation in the ironing cloth. So here is the question. The base of an iron is constructed from a 10 millimeter thick copper brick having conductivity of 386 watt meter hour. Okay, and then the measurement are made after a man is ironing. The plug was switched off, reveal temperature of 220 degrees Celsius and 180 degrees Celsius at the outer surface of the copper plate respectively. So we are going to calculate the cooling rate through a copper plate of the iron that has a surface area of 200 cm square. So the solution is, first we list the information given. The thickness is 10 millimeter. We convert it to 0.01 meter, and the surface area is 200 cm meter cube. We convert it to meter cube, that is 0.02 meter cube. And then we have the temperature in the inner surface of the plate, that is 220 degrees Celsius. We convert to the Kelvin, plus 203 Kelvin, we got 490 Kelvin. And then for the temperature in the outer is 453 Kelvin after we convert. So since the heat transfer to the copper plate is by conduction, the heat flood may be determined by the Fourier's law that we got. Q double naught that is equal to K delta T over L. So after that, we insert the value that we have listed before, and then we got 1,544 kilowatt per meter square. And then the heat flux, but this is not the final answer yet. The heat flux represents the rate of heat transfer to a section of finite area. So we need to multiply it with the surface area, that is 0.02 meter square. So after we multiply 1544 with 0.02 meter square, we got the Q equal to 30.88 kilowatt. So that's the answer.
So next I will explain the industry application for counter flow cooling tower. So as you can see in the picture, uh, there are some arrow. Blue arrow indicate the flow of air, and there also the pink color. So it indicates the flow of water. So we go for the flow of water first. So as you can see, uh, uh, hot water will enter through the top of tower. Hot water from machine or whatever will enter through the top of tower, and then it will go to water distribution deck. After that, the water will spray out of nozzles, and it will go to the coil or field. Basically, this is a heat transfer, a heat exchanger in the cooling tower. After that, it will fall into the cooling tower basin, and after we go to the basin, uh, at the bottom he has the suction power, suction pump suction to suck the water, and water will repeat the process again. So next, so for the flow of air, first the air will enter through the base of tower at the bottom. Then it will drawn up to the field heat exchanger, and it will flowing outwards and away from the cooling tower. So the flow of air is more simple than the flow of water. Next, so the flow of heat exchanger in cooling tower. So in the cooling tower, the water are going down due to gravity. The air is being drawn up by a fan. So these two is counter flow each other because there is 180 degree to each other. So we can say that the flow is counter flow. So in this, cooling effect can occur due to the air is cooler than the cooling water. However, what's the doing cooling here is evaporative cooling. Some of water as it pass through the heat exchanger is going to evaporate. So it's actually gonna cool the water molecules that surrounding it. So that's all for concept of heat exchanger.
So thank you, Abdullah. So I will continue with the calculation of the example of cooling tower. So the question is, a double pipe heat exchanger is used to cool a heat transfer fluid from 410 Kelvin to 330 Kelvin using cooling tower water. The heat transfer fluid flows through the annulus at a mass flow rate of 0.22 kilogram per second, and it has a specific heat capacity of 1740, and the flow condition provide that the heat transfer coefficient associated with heat transfer fluid is 895. On the other hand, cooling tower water enters the inner pipe at 285 Kelvin and at a mass flow rate of 0.32 kilogram per second, and with specific heat capacity of 4195. And the flow condition provide that the inside heat transfer coefficient is 5760, and the inner pipe of the double pipe has exchanger has dimension of 20.9 millimeter, which is inner diameter, and 26.7 millimeter of outer diameter. And the pipe is made of a material whose thermal conductivity is 15.4. It is given that volume factors are 9.2 times 10 to the power of -5 for tube side fluid, and 8.5 times 10 to the power of -4 for annulus side fluid. So the heat loss is given as a 30624 watts. So the question are, what is the outlet temperature in Kelvin of cooling tower? What is the overall heat transfer coefficient based on the inside area? And what is the length in meter of the heat exchanger configured to operate in parallel flow? So first we must show the diagram and list out all the information from the question, and then proceed to the calculation. So for the outlet temperature in Kelvin of cooling water, apply energy balance for hot fluid and cooling water. So the energy lost by hot fluid is equal to energy gained by cold fluid, which is m dot c delta T equal to m dot c delta T. So after we substitute all the value, and lastly we can get the T cold at the outer part is 303.812 Kelvin. So for the next question is, what is the overall heat transfer coefficient based on the inside area? So for overall heat transfer coefficient based on the inside area, we have the equation for the UI, which indicates the U in the inner tube. So this is the equation. Yeah, this is the equation. And after we put the equation, we substitute all the value. And lastly, we get the overall heat transfer, which is 507.16 watts per meter squared per Kelvin. And for the last question is, what is the length in meter of heat exchanger configured to operate in parallel flow? So LMTD is log mean temperature difference, which has a formula of delta T inner minus delta T outer divided by ln delta T inner over delta T outer. So after we substitute all the value to the formula, we get the log mean temperature difference, which is 59.471 Kelvin. And so we're using the LMTD method. So Q loss will equal to UA times by log mean temperature difference. So it is given from the question that the Q loss is 30624, and the area, which is 2 pi diameter inner L. So we rearrange the equation, and lastly we get the length of the tube, which is 15.463 meter. So I think that's all for our presentation. Thank you very much.